All right, and did we confirm that Miriam can hear us okay? And
Let me see who's there.
Dr. Lurs Hall Ness, can you hear us okay?
I can hear you.
Yep.
Thank you very much. Okay, all right, let's get started. I'll have to maybe push down a little bit. So it is my great pleasure to introduce this year's William R. Thompson Distinguished Lecturer, Dr. Andrew Cameron. Dr. Cameron's connection, he comes from Johns Hopkins, and his connection to Johns Hopkins began quite literally. I believe he was born at Johns Hopkins Hospital and raised in Baltimore. He went on to attend Harvard before returning to Johns Hopkins, where he earned both his medical degree and his PhD in neuroscience. He then trained in general surgery at Mass General, and then went across the country to his transplant fellowship at UCLA before returning to Hopkins in 2006 as head of the liver transplant program. Today, Dr. Cameron is the William Halstead Professor of Surgery. He's the Surgeon in Chief of the Johns Hopkins Hospital, Chief of the Division of Transplantation, and the 8th Director of the Johns Hopkins Department of Surgery. What makes Dr. Cameron's career especially fitting for this lectureship is not simply the titles, it is the breadth of the work, the intersection of GI surgery, transplant, research, ethics, and innovation. He's built a major clinical and academic career caring for patients with alcohol-associated liver disease, hepatocellular carcinoma, and end-stage liver disease. And he also has a NIH-funded research lab where he studies severe alcoholic hepatitis and transplant for alcohol use disorder. His work also addresses one of the central challenges in transplant, which is the organ shortage. He's led efforts to improve access to organ transplant, including novel public-facing efforts using social media to increase awareness. He also does a lot of work in xenotransplantation, which I know is one of the things we'll be talking to us about today. In many ways, Dr. Cameron represents both the history and future of academic surgery, Hopkins surgeon in the Halstead tradition, but one whose work is focused on the next area of transplant, access, innovation, and compassionate care. Please join me in welcoming Dr. Cameron.
Brent, thanks very much, and thanks Rory as well for having me. It's a real pleasure to be here. I will 45 minutes of your time this morning and walk you through some interesting stuff that's going on in Baltimore and around the country, and we'll talk about sort of a major public health problem and what may be a potential solution. It is certainly an honor to be here for the Thompson Lecture. We are all getting up in the morning to serve our patients, and no better example of service than Dr. Thompson, Lieutenant Commander in the Air Force, one of your chief of surgery on 2 occasions. It's a real honor to be here today. And I'm just happy we got the slides up. Let's see. How do we advance it?
We have like one presentation.
You know what I could.
One more time with the minutes.
Oh, perfect.
There we go.
Got it. All right, let's try it again. So in order for me to tell you about this new idea, I have to tell you everything I know about transplant, but luckily I can do that in just 2 minutes. So here's everything I know. It started here, not too far away from where we are right now. The first organ transplant ever was up at the Brigham in 1954, done by that guy in your upper left-hand corner. That's Joe Murray. You can see his first 2 patients. You'll notice a similarity between those 2 guys. They were identical twins. And that's how Dr. Murray sort of got around the central challenge of transplant, which is the allo response or rejection. There's the famous picture that hangs in Count Wayne Library commemorating that first important transplant. And there's actually a wonderful book that Dr. Murray wrote about this. I had a chance to meet Dr. Murray a couple times. But that's just to show you, before him, there was none, and he was our clinical generation. So that's how recent transplants. All right, fast forward. This guy is personal hero to many of us. That's Tom Starzl. First liver transplant ever was 1967. There's a picture of Dr. Starzl when he was an intern at Johns Hopkins, standing behind Dr. Blaylock. And there's a picture at a more recent visit. We were lucky enough to have Dr. Starzl back. Same deal. He was a guy you could meet and talk to, and he himself sort of almost single-handedly started liver transplantation. And there's a wonderful book about that too, that most of us in transplant have read and would heartily recommend. All right, we're almost there. So then nobody, I hate to say it, really cared about the first kidney or the first liver transplant. I'm not many people knew what the liver did, but the first human heart transplant, the public sort of tapped in, to the spiritual significance of transferring the human heart, was done by this very broken individual, Christian Bernard, interestingly, in Cape Town, South Africa. And there's a fantastic book about that too. It's almost a Hollywood story about who was going to do the first human heart transplant, and the public sort of followed along with great interest. All right, you got it? That's the history of transplant. But what you should know is it didn't work. They could, you could sell them in, and then everybody died because they all died of rejection. And there was serious thought put into a worldwide moratorium on all organ transplant in the 70s. They were just going to stop. It just didn't work until this. And that's Burrell, and that's cyclosporin. And the discovery of cyclosporin was the key event in the history of all transplant, the most potent immunosuppressive ever discovered, 100 times more potent than steroids. And with cyclosporin, transplant worked. Okay, so here's New England Journal in 1981. There's our friend Tom Starzl, his article, Liver Transplantation with Use of Cyclosporin. So the year before Starzl got cyclosporin, his 1-year survival for liver transplant was 33%, which is to say everybody died. When he started using cyclosporin, the 1-year survival the year after was 83%, which is to say everybody lived. If you looked at the UNOS database last year for transplant in the US, the survival was like 91%. So everything changed in 1980, and very little has changed in the subsequent 50 or 60 years. That's how important the immune response is. You got it. That's it. That's the history of transplant. Now, so transplant takes off, cyclosporin, the drug that works. There's a book about that too. It's actually about FK506 or tacrolimus, which is what sort of son of cyclosporin, which all transplant patients get. And this is it. It went from not working, we should give up on it, to the figure you see here. You can see it from the back of the room. The line going through the roof is the number of patients waiting, in this case for a kidney, it's 100,000 Americans. And the flat lines going nowhere at the bottom are the number of transplants we do every year. So the history of transplant is it didn't work, cyclosporin hit, and now there's a line around the block to get a life-saving organ transplant. And if you've met a patient on dialysis, you know how miserable that is. And if you get a kidney transplant, there are guys that play in the NBA after a kidney transplant. All right, so this is all that's worth talking about in transplant, is how do we get more organs? That's the problem. It's a public health crisis. So let's talk solutions. That's what we're going to talk about today. All right. Potential solutions. We could increase donation rates. How about we just do that? That sounds a lot simpler than animal organs. This is a college friend of mine. This is our 25th college reunion. This is Sheryl Sandberg. She was the COO of Facebook. And we got together to collaborate on the organ donation shortage by changing do you guys even know what Facebook is? Anybody? It's kind of like TikTok sort of. Anyway, on Facebook, she agreed to change the platform so you could specify, like where you went to college or what music you like, that you were an organ donor. And when you did that, all your friends got the message, Andrew's an organ donor, you ought to do it too. And they got a link to their state database to register for organ donation. This is what it looked like. You should do this too. And when we did that, we saw a big uptick in online donor registration. And of course, those media campaigns have a half-life that can normally be measured in hours. So living donation could be a good option, especially for kidney transplant. We went back to Facebook and we created an app. You could download the app and it would drag you through a social media post. You don't know this about me, but I'm on dialysis. Click here to learn more. Click here to contact my transplant center and initiate a donor evaluation. And with that app, we gave it to patients at Johns Hopkins who had been on the wait list for at least 2 years without an organ donor. The folks that got the app were 7.7 times more likely to have a donor come forward than a control group that didn't get the app. So So it helped a little, but as here we are today, it didn't fix the problem. Implantable machines, implantable dialysis machines, artificial hearts, could that be the solution? Stem cells to repair damaged organs, 3D printing, I'm sort of here for any and all of it. What we'll talk about today is the possibility of using animal organs as a solution to the donor shortage. And that's xenotransplantation. All right. Animals for transplant is a very bad idea. It has obvious disadvantages. In fact, it almost for sure won't work. We all, if I were to put a pig kidney in you today, like a farm pig, you would reject it in 2 minutes. We all have preformed anti-pig antibodies, which is sort of interesting why we would have that. But we do, it won't work. It's not, we talked about this at dinner last night, it's not even entirely clear that an animal organ would work the same way that a human transplant would to save your life. Maybe a heart would pump, just pig heart would pump fine, but would a pig kidney do the same thing physiologically? Would a pig liver recreate all the human proteins that a human liver makes? We just got over COVID, which was the worst pandemic in 100 years, and it was when a virus jumped from animal to human. Are we going to unleash COVID 2.0, with animal organs? And it may be that you just don't go for this. It may be that you think this is an inappropriate use of animals. And we could talk about that too. So it's not a very good idea. On the other hand, if it worked, it would be the solution. It would be an unlimited supply of organs. So there's 100,000 people waiting on the kidney list, but there's 500,000, 500,000 Americans on dialysis. People die waiting for hearts and livers. This problem would be solved. In some ways, pigs would be healthier than the organs we transplant for humans. So when we go out on a procurement, it may be an 80-year-old. It may be somebody that's morbidly obese. And you sort of get what they're all have undergone some traumatic experience where they've died. These pigs would be perfectly healthy living donors, selected and bred to be perfect for transplant. And in some ways, they might be less risky. So I transplant livers with Hep B, Hep C, and in some cases HIV. And pigs don't get any of those viruses. And pigs would be kept immaculately clean of viruses, and in some ways would represent a very low infectious risk. So it's worth considering. But like I say, it's not going to work because we all have anti-pig antibodies. And that's interesting. It's not because you eat pork or you're around pigs. When we are born, we don't have these antibodies, but your gut gets colonized with microbes against which you develop antibodies, and some of those antibodies cross-react with an antigen that pigs have that we don't. Got that? So it's kind of weird and complicated, but it's an evolutionary phenomenon. This was all figured out by Big John Najarian, who played football. But this is the problem. You have anti-pig antibodies against an antigen on pig endothelial cells, and you hyperacutely reject pig organs. So again, forget it. It's not going to work. Now, before I go any further, it wouldn't have to be pigs. So we could use non-human primates as donors. Monkeys, chimpanzees, baboons. And if I put a chimpanzee kidney into you today, it would work perfectly. So that's one take home is non-human primates, baboons, for example, are very, very, very similar to humans. So similar that we could use them for transplant, and that would work. So why don't we just do that? Baboons would work immunologically. The problem with baboons is there aren't enough baboons to go around. We would use up all the baboons in captivity very quickly, and we need a solution which will help 100,000 people. And baboons are born one at a time like humans and have to grow years and years to reach donation age. So baboons are going to be logistically no good. They're a little bit on the small side. Their physiology would be good. You can't genetically engineer baboons, which is what we'll talk about today. Because they are so similar to humans, the infectious risk would actually be higher, and just nobody's going for baboons. If you've ever worked in the lab with a baboon, they're very, very human-like. And it's just, I think would be ethically unacceptable in the population for baboons. All right, brings us back to pigs. Pigs have this deal breaker antibody, which makes it no good. Pigs would be available in unlimited supply. Pigs are born 8 to 12 per litter, and they reach donation size in 6 months. So pigs would be good logistically. The size would be good. I think the organs would work okay. We could talk about that. We'll talk today about this. You can genetically engineer pigs. We interact with pigs all the time on farms. The infectious risk of transmission is actually very low. And we've already gone for it. 100 million pigs are slaughtered every year in the US for food. So we've already sort of crossed that bridge. And I think 100 million and one for a kid with biliary atresia would be okay. So I think the public would go for pigs. All right, if this all sounds sort of bananas, it's actually already been done. This is before the time of a lot of people in this room, but this is Leonard Bailey, who's a pediatric heart surgeon in Southern California. And that is baby Faye in 1984. I got a chance to meet Leonard Bailey too. I was a fellow at UCLA and I did a procurement one night at Loma Linda. This is the picture that hangs in Loma Linda, this hospital in Southern California. That's Leonard Bailey with all the lives of the kids whose lives he saved. That's baby Faye in 1984 in Los Angeles. Leonard Bailey put a baboon heart into baby Faye. And again, it sort of captured the public imagination and everybody followed along. And unfortunately, it didn't save baby Faye's life. She only lived 14 days. So it's been done, but not successfully, and it's been dropped because it didn't work. That was 50 years ago. Okay, well, it's been done. It's been done a couple more times. So here's what I was mentioning. This is Keith Reemsma, who in 1964, so way before even cyclosporin, put chimpanzee kidneys into people in New Orleans, and a couple of them lasted almost a year. In 64, this is the guy on whom Hawkeye Pierce was based. You guys ever heard of MASH? No, MASH. It's a TV show. TV. Yeah. Okay. Thank you. So that was a surgeon in MASH based on Keith Reemsma. I mentioned Leonard Bailey. 14 days, and then here's our friend Tom Starzl again, who put a baboon liver into a patient in Pittsburgh, which lasted a couple months. There's Starzl. And he trained this guy on my right, Ron Busuttil, and that's who I did my liver transplant with. So it's been done, but it's been dropped because it didn't work. All right. Big breakthrough. So early 2000, this wonderful scientist, David Ayers, created a knockout pig. So you've heard of a knockout mouse, that's totally no big deal. You can pay $1,000, the knockout mouse arrives in the mail. Knocking out a gene in a pig is a huge deal. It took him 10 years to knock out a gene in the pig. And the gene he knocked out was the gene, the enzyme that puts the antigen in place that we all have these antibodies against. So he had created a herd of pigs, it took him 10 years, that were going to be perfect for transplant. And there's a picture of David Ayers when he came to Hopkins to give grant rounds. And so a lot of excitement. And the short version of the story is that these animal organs that were lasting only minutes, with this knockout lasted hours. So no good. So heartbreak again, Xeno, not going to work. The future of transplant always will be. Knocking out one gene and one antigen simply revealed the presence of a couple other antigens that we hadn't seen because most of the antigen was from this enzyme. All right, so despair again. And now here was the real game changer. I'm sure everybody in the room knows CRISPR-Cas. It is very, very interesting bacterial antiviral defense mechanism, which is very efficient at chopping up DNA and RNA. And great book about that. Jennifer Doudna from Berkeley sort of was one of the main discoverers of CRISPR-Cas. There's her collecting her Nobel Prize. Very controversial what we should do with CRISPR-Cas. So with CRISPR-Cas, editing genomes became very, very efficient. So what should we do with that? Should we take babies and edit the HIV receptor so no kid ever gets AIDS again, very controversial. But what was not controversial was editing animal genomes. Everybody was going, that was fun. So here's George Church up at Harvard. So when is this? More recently, 2015. So it took David Ayers 10 years to knock out one gene. This is George Church knocking out 62 genes with CRISPR-Cas. So you can sort of just dial in and dial out whatever you want. Which brings us back to the pigs, which now have not one genetic edit, Dave Ayers, they have 10 genetic edits. So here are the pigs. And they have this work we do in collaboration with a big biotech company, Revivicor, which is part of United Therapeutics. Here's these pigs have 10 genes knocked out, or you'll see 4 knocked out, 6 knocked in. Here's the first one that David Ayers knocked out, and that revealed the presence of more antigen. When we knocked out these other 2 enzymes, you now have cleared out 95% of the antigen against which we have anti-pig antibodies. So in addition to 3 knockouts to make the animals less pig-like, you knock in 6 human genes to make them more human-like. And these are complement inhibitors, genes to prevent the organs clotting off, anti-inflammatory immunosuppressive genes. And as you can see, you can pretty much dial in anything you want to make these pigs good for transplant. There was one more gene they knocked out, which is sort of a weird story. There was concern, if you've ever seen a pig on a farm, it's gigantic. And there was concern that when you transplanted a pig heart, the heart was going to keep growing and growing and be too big for the human recipient. So they knocked out the porcine growth hormone receptor so that the pigs wouldn't grow. And again, if this all seems very, very far-fetched science fiction, that's the pig. That's hopefully going to change the world. All right, this is sort of big business. Here's this Revivicor that we collaborate with the 10GE pig. There's eGenesis, which is the Harvard team working with Mass General. Makana is Joe Tech. I mean, it's going to be, a lot of companies that are interested in producing these animals. And with CRISPR-Cas, it's very, very easy to do. It used to be hard, now it's easy, which is exciting. All right, let me tell you the more recent version. So maybe you've heard about this. So this guy on the right with the NG tube is Mr. Bennett. And that's his heart surgeon, Bart Griffith, a friend of mine at the University of Maryland. Mr. Bennett was in the Maryland cardiac SICU just down the street from Hopkins. Dying. And he was on ECMO and he was on 3 pressors and he was going to die. And they determined at Maryland that he wasn't a candidate for a human heart. He was, just going to die. And they offered him a 10GE pig heart. And they did his transplant. The FDA, to everybody's shock, said, give it a try, because there's nothing else to do. And Mr. Bennett got a pig heart, and it worked. It worked like crazy. His heart worked great. Mr. Bennett came off ECMO. He got off pressor. His heart worked so well, he had to go on antihypertensives. He extubated. He was walking around the Maryland SICU, and I thought we were done. I thought Mr. Bennett was going to throw out the first pitch at Camden Yards. I was never going to have to get up again in the middle of the night, and transplant had been figured out. And about a month into it, Mr. Bennett's heart stopped working, and a month later he died. And it was devastating, obviously, for the patient and his family, and for the team and for the field. But as you can imagine, it was very, very carefully studied, the case. And it was interesting because Mr. Bennett, on autopsy, hadn't died of rejection, which was exciting. He had died of a virus. He died of porcine CMV. So it turns out, we all have CMV, but we have human CMV, and this was pig CMV, which doesn't infect humans, it only infects pigs, but it had reinfected his pig heart and caused it to stop working. And it turns out that the heart that he got from the pig had latent CMV. And that is something that we need to learn from and can study. And now there's a more sensitive PCR test, and we know that the herd doesn't have CMV in There are drugs, antivirals that can be used for CMV. So, progress. In fact, there have been 9 what I'll call modern xenotransplants in the sort of modern age of 10 GE animals. So Maryland did another heart, and that guy also lived 2 months and died, and he did die of rejection. So he bled, and they gave him FFP, and FFP has a ton of antibodies in it, it turns out, and that caused a rejection episode. So again, choppy waters as we learn what's going on. There have been 7 kidneys, 10G xeno kidneys transplanted, 3 at Mass General and 4 at NYU. And the first kidney was done at Mass General, and the guy did fantastic. He got a creatinine of 1, he went home, he was a Boston bus driver, and he was about to go back to work. And he died in his sleep 2 months later of an MI. And it's not clear. Was that related to a xenotransplant? Probably, but it's hard to know entirely. Kidney transplants can be sick for a variety of reasons. So the longest amount of time somebody has gone with a modern xenograft is 9 months, again, up in Boston. They did another kidney xenotransplant. The guy literally did throw out the first pitch at Fenway. But his graft sort of stopped working at 7 or 8 months and it was removed. Now, I'll mention a couple other things before I get into what we're doing at Hopkins. So there's another way to test xenografts besides just putting them into people and see what happens. One of them is what's called decedent work. So if you die, God forbid, and you want to donate your organs for transplant, if you're medically inappropriate, like you died of a metastatic melanoma or something, you can't donate, but you could still serve as a recipient. So if there's a brain dead person in a unit being kept going, they could be used as a recipient for a xenograft. And that was what was done at NYU and UAB. They transplanted the xeno kidney into a brain dead decedent and followed that organ for 2 months to see how it would do. And there was a xeno heart done, and Penn did an interesting thing where they took decedents and they hooked them up in a cross circulation experiment to a xeno liver and were able to show that the decedent had improved liver function. All right, so you get the idea. You could do clinical trials, which I mentioned. You could do decedent work, or another way you could study xenografts, which we think is a good way, is large animal models. So I mentioned how similar baboons are to humans. Another thing you could do is take a genetically engineered pig kidney and put it into a baboon and make sure that it works before we, put it into people. And that's what we do at Hopkins. All right, so here's some of the press, which maybe you've seen some of this. The press is sort of surprisingly friendly, as is the public. It's, I think, a testament to how bad dialysis is and how desperate our patients are as they wait for an organ transplant that statistically is unlikely to come. Here's the decedent work, which was done at UAB, and here's Bob Montgomery at NYU in the New England Journal for 2 decedent kidneys he did early on. Interestingly, those were not the 10GE modern pig. That was the single Dave Ayres knockout. But they co-transplanted the thymus, which is an immunoregulatory organ, which is thought to promote tolerance or less need for transplant meds. Interestingly, all the work I've talked about is being done in the United States. You might imagine that this would be done overseas as well, like the first human heart transplant, where perhaps there are less regulatory barriers or oversight, but it's not really been the case. There is some work going on overseas, but most of it has been done in the United States thus far. But I still think we may wake up and find out that there's been a xenotransplant in China or Japan or South Africa that's been successful. All right, so here's what we do at Hopkins. Maybe 5, 6 years ago, we recruited Dr. Yamada, shown in the white coat, from Columbia, previously at Harvard, who has been sort of a xeno thought leader for decades. And Kaz pursues xenotolerance. So he transplants genetically engineered pig kidneys into baboons with the thymus. And with that, those organs last not minutes, not hours, but out a year with normal renal function. And he published that in Nature. So bringing xenotransplant to your hospital, it turns out it is a big deal. And it takes the approval of the dean and the president and all the leadership to say that this is something we think we ought to be doing. And we brought a cousin a couple of years ago, and he now has a huge, large animal lab that does a number of xenotransplants every month. All right, and the reason why, one of the reasons why we're doing this is to get approval from the FDA to do a human trial. So there is governmental oversight of xenotransplantation. It's via the FDA. And they will allow a human clinical trial, they told us, if they saw these pig kidneys working in baboons for 6 months. So if you could transplant a pig kidney into a baboon and the animal had good renal function at 6 months, they'd let us try it in people as part of an FDA trial. And that is what we've been working on for the last couple of years. So here's what those experiments look like. We get up in the morning in Baltimore and we go on an organ procurement as if it was a human transplant. We fly to Blacksburg, Virginia Tech, which is where the farm is with these genetically engineered animals. And then we fly back to Baltimore. So here's a picture. I'm going to get the kidneys. Bart Griffith, the guy I showed you before, is going to get the heart. We'll fly back to Baltimore. Kaz will put the kidneys into baboons and Bart will sew the heart into a baboon over at the University of Maryland. And every time we do one of these xeno experiments, it costs $1 million, which we can't afford at Hopkins. But we got a huge grant to fund this work, and we've been doing a bunch of it. And here's Kaz's team. And here's they did it, and they were able to pull it off. And here's the results of that publication. So this is to show that all the genes that were supposed to be knocked out are gone, and all the genes that are supposed to be knocked in can be seen in these 10 GE pig kidneys. And here's the survival of the animals. It's kind of interesting. Sure enough, for 6 months, the animals lived and had great renal function. But I got to admit, after about 6 months, they started conking out. And they started losing their graft function, but to things we thought we could probably treat in humans. They developed adenovirus infections. They stopped taking their tacrolimus. You can't do plasmapheresis, on a baboon. So we thought it's good enough for the FDA, and I think we could do better in people. But it's interesting. I mean, in the animals and in people so far, it's been hard to get past about 6 months of survival. And whether that's an incredible accomplishment or still not nearly good enough, is up for discussion. So as I start to sort of wind down here, we are getting close, but I think there are still obviously, obstacles before this is ready for prime time. So rejection, I think we're doing well on actually. You can do cross matches. You can select patients that have relatively few anti-pig antibodies. We've got these animals that don't have antigen anymore. We're getting complement is activated by xenograft. We're very good at inhibiting complement. We're getting there on rejection. Are these grafts going to work? And save lives and physiologically function well enough to be worth it? TBD. I think a pig heart is going to work great because it's just a pump. I think a pig kidney is going to work well because it's kind of just a filter. Pig liver, pig lungs, down the road. Is it safe? I think this is sort of a yellow light. We've got to make sure that we don't hurt people in the name of trying to help them. Is it safe for the patients, but is it safe for everybody else? If they go to the grocery store or the movies, are you at risk if you're sitting next to them? Is it safe for the caregivers that are participating in the care of xeno recipients? And then the last thing I'll sort of get into is this scalable? So when we started to talk, we were supposed to be proposing a solution for 100,000 people. If this is something you can only do at Mass General, in a place like this, and it costs a couple $1 million, that's not going to fix the problem. It has to be something that's going to work and is sort of democratizable and implementable and disseminatable. And Xeno's sort of got to walk before it can run. All right, a word more on scalability. So how is this gonna work? Like, are these pigs coming to Hopkins? Are we gonna fly down to the farm and get them every time? It turns out you're probably gonna have to fly down to the farm, which is gonna be an FDA approved facility. There's probably gonna be farms all over the country. And you're gonna have to bring the organs back to your center. And we have data that these xeno organs are very finicky and they don't like to sit in the cold cooler very long. In fact, we've had success pumping them. So I don't know if you guys pump organs here, but normothermic machine perfusion. Rather than taking an organ out and put it in the cooler, you put it on essentially a mobile heart-lung machine and you pump warm oxygenated blood through the organ while it awaits transplant. And this has been a huge step forward for liver transplant, for example, using organs that we never would have used and knowing will work because they pump well. There's a couple of different sort of varieties of the pump. And again, the pump is really expensive. Every time we use it, it costs a ton of money, but it is good for our patients and it may be essential for Xeno as we try to logistically figure out how we're gonna get these animal organs where they need to go. All right, last couple thoughts here. So again, if this is gonna cost a lot of money, and if it's gonna be controlled by for-profit pharma companies, I'm not sure that's gonna be a good solution. I do, we talked about this last night too. I do worry that if for-profit companies get control of the organ supply, right now, people donate their organs out of the goodness of their heart and fair-minded, equity-thinking doctors distribute them in a way that's fair and transparent. That may be really fractured if the organs are just for sale from a company that's here to make profit. And we may lose control of organ transplantation if we're not careful. So here's my solution for that. We are gonna make our own pig. So this is Jonas Salk, who figured out the polio vaccine. And the press asked him, hey, this is gonna be great, you're gonna be rich, you're gonna patent it. And he said, I'm not gonna patent it, I'm gonna give it away for free. Could you patent the sun? There's a great book about that too. And this is where I think we need to go with these animals, because right now they're controlled by biotech companies. And yet I'm telling you, CRISPR-Cas, you can do it, in your garage. And so we are making our pig at Hopkins with we have a notion that some of the things we've learned from these companies, there's no way the current pig is going to be the pig. This is like pig 1.0, and there's going to be a 2.0 pig with a different permutation combination of genes in the near future. Some of which like that growth factor knockout, that was a bad idea. The pigs don't really grow, and that makes the pigs frail, unable to grow, unable to breed, and the tissues in xenografts are weird. The blood vessels, because of the growth hormone receptor knockout, the vessels are weird and the ureter is really friable and hard to sew. So there's going to be better pigs, and we're going to make one at Hopkins. And we have a very clear idea of the genes which have to go and the genes which we want to knock in. And we're probably going to have we're doing it in collaboration with the NIH, which is always the way to go. And I think we're going to have a better pig maybe on the ground in like 6 months. And we're going to give it away. We're not going to sell it. So let's finish up here with sort of the risks. There are these obvious, very specific risks of, are you going to unleash COVID and is it going to be safe, which need to be taken very seriously, and the government is serious about it. And then there's sort of the ethical question, which is just because we can do it, and I think we can do it. I think we can do it. We're going to be able to do it in a couple of years. We're almost there. But like if my daughter needed a kidney transplant, would I really want her to have a pig right now? And if the answer to that is no, why are we doing it in our patients? So somehow we have to get from where we are now to where we're going to be in 10 years when it works. And again, there's going to be some choppy waters in between. So, kind of who goes first is the question. All right. Here's the deal with who goes first. So all the transplants that I've been telling you about, the guys at Maryland, the patients at Mass General, that was done under emergency one-off Hail Mary approval. The FDA said, okay, you can do this one case. And if it's a success or failure, it's not going to lead to FDA approval of these grafts, for widespread use. That's EIND. Okay, what we're talking about now is a clinical trial. That's why we did that animal work, and that's what's going on now. So we collaborated with United Therapeutics to do this animal work and then submit to the FDA for a big clinical trial. That was accepted, and the trial has now been initiated. So who will be allowed, what's the inclusion criteria for this FDA approved trial? So there's two groups of people. This is the answer to who goes first, at least in this big clinical trial. It's going to be 50 xenotransplants. There's two groups. The first group are people that got to know. So you have renal failure, you're on dialysis, and Johns Hopkins or whoever told you you are not allowed to have a kidney transplant. There's some preclusion. You'll never get one. You're on the bench. Dialysis for the rest of your life. Those people could have a xenograft instead and get off dialysis. The other group are people that have been approved for kidney transplant at Hopkins, could maybe get a transplant tonight, but we know they are statistically more likely to go untransplanted or die in the next 5 years than get a kidney transplant because of their blood type and sensitivity and all that. So these are the people that potentially could participate and get a xenograft. So what I did was I called 30 people, sort of cold called them. 15 from the group that had been told no kidney transplant for you, 15 from the group that had been told you're not going to get one in a long time, and asked them, do you want to come in and meet me in clinic and enroll in my Xeno trial? 30 people. So I got 28 yeses. I'll be there tomorrow. I got one no, you're crazy, I would never want to do that. And I got one guy that said, I'll do it, but I don't want to go first. Why don't you do a couple and then call me back? And that guy's the smartest guy I talked to. And that's sort of what we're doing at Hopkins. We're not going first, but we have all this sort of institutional preparedness that we're doing, and we're probably going to do our first person later on this year. So we're undergoing sort of careful patient selection, institutional readiness, because we want to make sure that it's done as safely as possible. All right, here's my last thought. What I kind of worry about is that is this emerging success story, but I feel like it's going to be good, but not quite good enough. I feel like the patients sort of conk out and the animals conk out around 6 months, and I don't think that's good enough. If you need a kidney transplant, you're going to get a xenograft that works for 6 months. So it may be a big step forward, but again, I'm not sure it's quite ready for prime time. So what are we like? What if that's the case? How are we going to fix this? Are you just going to keep making new pigs and then putting them into people and see how that works? That doesn't seem like the right way to do it. That's kind of cumbersome. So what we're going to do at Hopkins is make this pig, this what I'll call a sort of base pig, which has 7 genetic edits that we know are essential. And then we're going to put those organs on the pump and knock in or knock out more genes and test those in baboons. So we're going to figure out, what genes are critical rather than just make pig after pig. So it may be that there's a standard set of knockouts that everybody needs. But then, for example, if you are going to get a transplant tomorrow, I'm going to take a pig organ, put it on the pump, and knock in your HLA into that graft. And that graft is just for you. And it may be that those last minute adjustments are what Xeno needs to sort of get over the hump. And that's sort of precision medicine for us. And we're doing that work at Hopkins. This is what it looks like. You take a xenograft out, you put it on the pump. You can deliver genetic cargo while it's on the pump, either with a viral vector or with nanoparticles, and show expression in the pig kidney before you put it into a baboon or a person. And here's what that work looks like. That's stuff we're doing now. All right, we did it. We talked about sort of past, present, and future. the history is, started up at the Brigham. And so whatever, 1950s, and here we are today. The present, where we're at now, is the number 20. So 20 people die every day in the United States waiting for an organ that never comes. Easily could save their lives. There just aren't enough organs. So we talked for an hour here. Somebody died during this time just because they didn't get a transplant. It's not some complicated cancer we can't figure it out. We could have saved their life, we just didn't have an organ. That's where we're at now. And that's the pressure to do stuff like animal transplantation. Here is our two small states, and between them, there's a couple thousand people waiting for an organ transplant. And the present is clinical trials in xenotransplantation. And that's exciting, though I think we have to be cautious, and I think we have to be careful, and we have to be always thoughtful of our patients first, besides just the New York Times or the exciting science. And the future, I'm hopeful, is a future that is maybe free of drug companies, in which scientists at places like this and our place can work together, for the service of our patients. And not for profit. So these are our transplant recipients at Johns Hopkins. This is why we do it, not for the New York Times, but for our patients. And this is the team at Hopkins. Nobody does this stuff alone. This is a giant team, team of surgeons, anesthesiologists. We've got our researchers. We've got an ID, IR, and in the middle of it all is Dr. Yamada. So with there, I'll quit. And again, I'll remind you while we're here today, and I'll say thanks a lot for having me.
Thanks, Andy. That was a very eye-opening lecture, I think, for many of us. For me, it's really kind of fun. Chris Law, who's over at Maryland, who's doing some of this stuff on the heart side, was a resident with me, and she kept doing xenotransplantation research, and it's just 10 years away, and actually it's now here, which is just really remarkable. Questions from the group? Yeah, go ahead.
So in your talk, I feel like a lot of it was about transplant as sort of destination therapy.
Yeah.
But particularly, I feel like people like were on the waiting list for a heart.
Yeah.
Do you think is a role for the xenotransplant as a bridge to definitive like human heart transplant?
Awesome question. Awesome question. So I like the way you're thinking, because there's this technology and it's kind of good, but I agree. I can't sign somebody up for a xeno and say it's going to work for 20 years. This is, which I can if I get a kidney transplant. So heart is funny, because if I give you a xeno heart and it stops working, you die. Unless I could get you another one, so a bridge, definitely a bridge for kidney. So I think as we sign people up, to be honest with them, we can't say it's going to last 20 years. It's not. Like if it lasts 6 months or a year, that's a win. But I do think we could tell them, you're not going to get a kidney transplant, or you're not going to get one for 5 years. Would you rather be on dialysis for 5 years, or I could give you a xenograft and you can wait for your organ, not on dialysis, but with a xeno in place. So let's say I put a xenograft in you and it worked, and then you don't go off the list. You still could get a call. There's a human organ for you, and we would bring you in, take your xeno out, and put the human in, and that would be a great use for it. Maybe same deal with people that need a liver transplant. We're going to put this, there's no organ for you tonight. You're going to die without a transplant. Here's a xenograft or a cross circulation xenograft. It's like liver dialysis. And then we're hoping to get a human organ for you. One interesting thing I'll say is when you put a pig kidney in somebody, you engender an immune response, and you engender anti-pig antibodies. And if that were to sabotage you for getting a human transplant, it would be a very bad thing. It turns out there is not cross-reactivity between HLA and SLA. So it doesn't hurt you to get a human kidney eventually, to get a pig kidney in the meantime. And vice versa. There are some humans that are very, very highly sensitized against HLA, either because from blood transfusions or pregnancies or previous transplant, they almost can't get a human transplant, but that doesn't mean they have anti-pig antibodies, and they may be appropriate for a xenograft. So there's some excellent immunologic opportunities, and you're right, it may be as a bridge before it's a destination therapy. I think that's almost for sure, because these things just aren't going to last 20 years until 20 years from now.
David?
So, what about a low stakes model to investigate, xenograft in humans? And being burn surgery, what about skin transplant?
Yeah.
So the red dot pig has great homology, it's our model when we do pig, burn experiments and knowledge. But planting a 10 by 10 centimeter full thickness, your genetically, your pig into a form, patient, and you can look at it, you can see it, you can biopsy it. And it's a low stakes model, because when that skin graft fails, you can take it off, and you've learned a lot. So what about using that as a low stakes way for iterative change for your model?
Great idea. So where we started, Joe Murray was a plastic surgeon. Got interested in immunology because he was studying pilots that got shot down in World War II, and he was doing skin grafts on them and studying rejection. Skin is obviously the most immunogenic organ that we would ever think about transplanting, which is why we don't transplant it, and people die of burns rather than just getting their dad to donate skin or something like that. I think that's a great idea. Pig skin coverage is already kind of used, but I think a benign xenoskin that has been engineered to not get rejected would be better. And I agree, it's totally appropriate because the stakes are low. The heart makes me nervous, transplanting a guy that it's not going to work forever, he's going to die. If he has no other option, I guess that's okay. I love the idea of a kidney, because if your kidney stops working, we take it out and you go back on dialysis. But I think skin is a fantastic idea, and the companies are thinking about that, and we are too. But I think as a biologic dressing, if nothing else, it's probably maybe better than what we have. And I think we could probably learn a lot at relatively low cost to the patient, which is key.
And the decedent cases are interesting, you didn't really
Yeah.
show this, but Montgomery's spinal kidney, he planted in the leg vessel so they could see the kidney and access it.
And biopsy it and learn from it.
Yeah.
And it's interesting and amazing that people consent to that, but you can learn a lot in those scenarios.
Yeah. Nick, did you have a question? All right, well, thanks, Andy, that was really great today. So, yeah.